The drift that shouldn't exist, the pioneer anomaly. Meanwhile, our own machines were still talking to us from the dark. Pioneer 10 and 11, launched in the early 197s, slipped past Jupiter, skimmed Saturn's domain and headed outward with nothing but radio as a lifeline. That radio tone was a heartbeat and a ruler in one. You ping a probe, it transpons the signal back, and the two-way Doppler shift tells you its line-of-sight speed to parts per trillion. Over years, those parts per trillion become miles of error, or victory. Here's why this matters. Deep space navigation is trust made mechanical. One missed force, one unmodeled delay, and a billion-dollar mission can skim the wrong hemisphere. The deep space network times the round trip and builds a world from those numbers. If something nudges the path or biases the tone, you won't see a mystery. You'll see a residual that refuses to flap. By the late 198s and through the 199s, analysts at JPL and elsewhere noticed a sliver of stubborn blue creeping into the Pioneer data. The Doppler residuals looked as if the spacecraft were experiencing a tiny, constant sunward acceleration, about 8.7 times 10 meters per second squared. Not a shove, a whisper. You wouldn't feel it in a car. Over billions of kilometers, it adds up. The checklist began. Solar radiation pressure pushes on the big dish. Model it better. Gravity from planets, the Kuiper belt, even general relativity's small corrections, include them all. Outgassing from thruster seals, maybe. Spin rate changes coupling to dynamics, perhaps. Then the engineer's favorite culprit, heat. Pioneer's radioisotope thermoelectric generators ran hot. If infrared photons radiated asymmetrically, say, bouncing off the back of the high-gain antenna, they could create a steady recoil. Warmth turned into thrust. For a while, the anomaly sharpened as more data came in. Papers speculated about modified gravity beyond Saturn, mound-like behavior in the outer solar system, drag from dust or dark matter. Others counseled patience. Spacecraft are messy. Clean up the housekeeping before rewriting physics. That became a campaign. Old telemetry tapes were baked and digitized. Attitude histories were reconstructed. Every watt of heat was traced from source to radiator. Teams built finite element thermal models and translated temperature histories into micronewtons. The thermal recoil solution gathered weight. Analyses showed that asymmetric heat emission could account for most, and in some reconstructions nearly all, of the 8.7 times 10 ms2. The leftover slivers wavered inside uncertainties tied to material aging and surface properties no one measured in deep space. The official mood settled. Not a new force, just a spacecraft telling us exactly how hard it was sweating. But even victory had seams. The models depended on assumptions about emissivity changing over decades, dust accumulating, spin axis precession, and complex reflections off braces and booms. Small correlations in the data, wiggles tied to Earth's rotation, station handovers, or Sun-Earth probe geometry, didn't always flatten completely. In hallways, you'd hear, "I'm 95% convinced it's heat," delivered with a smile that left room for the last 5. Then Earth flybys started whispering too. A handful of planetary encounters in the 199s and 200s returned tiny velocity mismatches, millimeters per second after gravity assists. Some flybys showed nothing. Others showed an energy change that didn't wash away with standard models. Analysts plotted declinations and azimuths, mapped tracking station transitions, and chased relativity corrections. Patterns teased, then slipped. Explanations ranged from modeling subtleties in Earth's gravity field and atmosphere to transponder frequency ramping and signal path calibration. The effect never rose to Pioneer's celebrity, but it kept the question alive. Are our signal models hiding edges? Here's the seam under the storyline. Two-way Doppler is a round-trip story. Earth sends a carrier. The spacecraft multiplies the uplink by a fixed ratio and sends it back. We compare the received frequency to the station clock. The beauty of two-way tracking is that it cancels a lot of one-way sins, independent clock drifts, some path delays and asymmetries. But it also buries the one-way path. If something subtle biases the outbound or inbound leg differently, ionosphere, troposphere, station electronics, or even our convention for aligning clocks, the round trip can look clean while the one-way hides a wrinkle we never measured directly. Human moments gave the anomaly its face. A navigation lead near Goldstone at 2 a.m., socks off in a motel room, stared at a residual plot that wouldn't lie flat, thought about his kid's spelling test, and shut the laptop, only to dream in Hertz. A young analyst spent weekends coaxing bits off magnetic tapes older than she was, labeling each file like a museum curator. In a conference coffee line, an old-timer muttered, "Space punishes certainty," and 3 people nodded like it was a prayer. In the end, Pioneer taught humility and craft. The best answer is that thermal recoil drove a steady sunward push of roughly the observed magnitude, with uncertainties that account for the rest. The flyby anomalies likely fold into station geometry, modeling choices, and small systematics that vanish as measurement campaigns improve. But the residue left a mark. Our navigation triumphs rest on exquisitely modeled physics and a quiet assumption. Two-way timing rules everything we trust, while the one-way path is a convention dressed as a constant. And that's why the neutrino night mattered. Different messengers, different channels, different buffers. Our instruments choose a zero and build a universe around it. Pioneer's whisper didn't break the limit. It pressed on the seam where we translate round-trip tones into one-way stories. Across town, in quieter labs, something even stranger was forming. Pairs of particles coordinating across distance as if a message had flown between them, without a message at all. The instant that isn't quantum entanglement's nasty habit. Across town from the deep space dishes, a different kind of antenna was waiting. Silicon avalanche photodiodes counting single photons, each click the softest footstep a particle can make. 2 nonlinear crystals, 1 pump laser and the strangest pact in physics, create a pair, send them apart, and ask questions they aren't supposed to answer until they've compared notes. Stakes first. Locality is the bedtime story that lets us sleep. What happens here can't depend on a choice made over there right now. Entanglement looked at that story and shrugged. Einstein, Podolsky, and Rosen set the chessboard in 1935. If quantum mechanics is complete, then distant particles share a state that makes their outcomes correlate too well, so well it feels like they're coordinating instantly. If that's absurd, there must be hidden instructions tucked into each particle at the start. 3 decades later, John Bell turned the debate into math. He wrote inequalities that any local hidden instruction theory must obey. Build an experiment that violates them, and the universe has to surrender either locality, realism, or both. Laboratories obliged. In the 198s, Elaine Aspect's team sent entangled photons through fast-switching analyzers, changing settings while the photons were already in flight. The results violated Bell's inequality. Critics pointed to loopholes. Maybe the sample was biased because detectors missed most photons, the detection loophole. Maybe the switching wasn't fast enough to prevent a slow, subliminal leak of information, the locality loophole. The response became a campaign. Better sources, brighter pairs, faster and space-like separated setting choices. By the mid-2001s, loophole-free became a deliverable. In Delft, experimenters entangled electron spins in diamond, read them out with high efficiency, and chose measurement settings fast enough and far enough apart to seal the locality gap. In Boulder and Vienna, photonic tests paired ultra-low-loss optics with superconducting detectors, shutting the detection loophole in the same runs where geometry sealed locality. The correlations refused to fit any local hidden variable script. Bell's inequality wasn't just broken, it was broken clean. Here's the nasty habit. Outcomes correlate across space-like separation, as if an update flashed between the labs. Yet messaging faster than light stays impossible. No signaling theorems say the marginal statistics on one side don't change when you twiddle settings on the other. You only see the pattern after a slow, classical comparison, and that comparison obeys C relativity survives. but every dataset looks like a conspiracy that cleans up after itself before you can catch it. Now the seam that ties back to our clocks. To call two detections coincidences, you need synchronized time tags. To prove the labs are space-like separated, you draw light cones using a C you only measure in round trips. The one-way alignment is a convention, Einstein's rule to split round-trip time evenly baked into your timing network. It works because the world is kind and the equipment is honest. But the bookkeeping reminds you, even here, simultaneity is negotiated, not discovered. Human beats kept the theory grounded. A grad student in a dark lab taped a note over a big red laser-on button that just said, "Breathe." A Pi sent an email at 2:13 a.m. We're over 5 sigma. A satellite pass for a free space link cleared. Someone cried from relief more than discovery. Later, teams used starlight from distant quasars to choose analyzer settings, pushing any possible collusion with hidden variables back hundreds of years. Cosmic randomness became part of the circuit diagram. The payoff escaped philosophy fast. Quantum key distribution turned entanglement's correlations into security. Tamper with the link and the error rate climbs. Teleportation protocols moved quantum states between nodes without moving particles, using pre-shared entanglement plus a classical message. Entanglement swapping stitched independent links into longer chains, the basis for quantum repeaters. Networks started to look like preloaded scaffolding. Pay up front in entangled pairs. Spend later when the classical sidecar arrives at light speed with the decoding key. Complication stayed honest. No signaling relies on assumptions. Independent setting choices, clean space-like separation, detectors free of bias. Loophole-free tests nailed them simultaneously, but never absolutely. There's always a residual someone can try to pry open. Philosophers reminded everyone about freedom of choice, the axiom that your random setting isn't secretly correlated with hidden variables. Cosmic photon randomizers helped, not because they prove independence in some cosmic court, but because they make any conspiracy absurdly baroque. Meanwhile, jargon hit a simple tension. We say no influence because no controllable message outruns light, yet the joint state acts like constraint rather than courier. Precompiled correlations make local updates land as if the world coordinated on a beat outside our messaging budget. If C is a refresh limit, entanglement is structure, the kind you install before the beat, then reveal after the beat when notes are compared. Microstories kept the 30-second rule alive. A postdoc set an alarm for a 3:07 a.m. satellite pass and whispered, "Come on," to her phone's live plot of coincidence rates. Another team broke into applause when their time tag jitter calibration finally held at tens of picoseconds. A philosopher brought muffins and left with more questions than crumbs. The field moved from spooky to service-level agreements. How many bell pairs per second at this fidelity, under this weather, across this baseline? This was the moment the instant that tisn't stopped feeling like a paradox and started looking like architecture. No bits move faster than light. Patterns do, in a sense that lives in correlations pre-installed across space, only readable after slow notes align. Our clocks, synchronized by a convention that works, sort coincidences into meaning. The wall stands for messages. The seam appears in how we define now to read the pattern. And that seam is about to matter even more when we talk about the rule that smuggled itself into our timing from the start. The assumption Einstein needed, one-way versus two-way light. To see why the instant that tisn't keeps getting away with it, we have to open the box almost nobody touches. There are two speeds of light hiding inside one symbol. The two-way speed, the outtan back you get from a ping and a reflection, is what we actually measure. The one-way speed, the straight shot from A to B, is what we assume when we set clocks. That move wasn't a loophole, it was Einstein's genius. It's also the seam the story keeps snagging on. In 1905, Einstein needed a clean way to glue distant events into a single timeline. He proposed a rule that feels obvious until you look closely. Synchronize clocks by sending a light pulse from A to B and back. Then set the clock so that the travel time is split evenly between the outbound and inbound legs. If the round trip takes t, you declare the one-way times t2 and t2. That choice, Einstein synchronization, bakes in that the one-way speed equals the measured two-way speed, c, in all directions. Philosophers later gave that choice a dial. Hans Reichenbach introduced epsilon, a parameter that tells you how to split the round trip. Epsilon equals 1,2 gives Einstein's symmetric split. Tilt epsilon away from 1,2 and you skew simultaneous in a direction-dependent way, while keeping the same round-trip c and the same local physics. If you rewrite all your equations consistently, observables tied to round trips don't change. You get the same experiment, the same radar distance, the same Doppler tracking. The world doesn't move, the bookkeeping does. Why should anyone care? Because our hardest problems ride on clocks. GPS works by comparing one-way signal times from satellites to a receiver down here. But under the hood, it's built to cancel the traps. It solves for receiver time bias, uses relativistic models for satellite clocks, and relies on a constellation tied to a global coordinate time defined by Einstein synchronization. Time transfer between national labs, fiber links, and satellite common view all inherit that same convention. It's not wrong. It's a standard. Standards are how the world functions, but standards are also choices. Here's the stakes in practice. Every time you call two detections simultaneous, you've already picked a way to align the tapes. Entanglement experiments trust picosecond time tags that were disciplined by a network using Einstein's rule. Neutrino burst comparisons between continents translate local times through GPS and geodesy into a world clock that assumes symmetric one-way light. Deep space navigation lives on two-way tracking, but when you cross-compare stations or fold in one-way ranging and time transfer, you step onto the same convention. Our universe of data is stitched together on a principle we chose because it makes the math sing and the missions fly. The predictable objection is right and misleading at the same time. If epsilon is just a convention, then nothing physical depends on it. True for round-trip observables, true for any local lab in free fall. But the interpretation of distant order, the sequence you write into the script when you say event A happened before event B across the sky, leans on the slice you picked. Special relativity tells you not to treat distant simultaneity as a fact of nature, it's coordination. Einstein's move made that coordination simple and isotropic. That simplicity feels like truth because it works everywhere we've looked. Metrologists live in this world daily. They fight picoseconds of dispersion in fibers. Forward and backward paths aren't identical. They calibrate two-way satellite time and frequency transfer to nanoseconds, while one-way delays soak up models of troposphere and ionosphere that don't perfectly mirror. In their notebooks, you'll find lines like assume symmetry to first order, residual asymmetry below XPS. It's honest, and it keeps the trains on time. It also marks the seam. We can measure the out and back. We can only define the straight shot. Human moments make the point stick. In a timing lab, two hydrogen masers sit like quiet metronomes. A technician routes a 10 MHz reference through kilometers of buried fiber and discovers the forward path lags the return by a hair. A colleague adds a dispersion compensator and writes assume symmetry in the log. They both know that assumption is the move that keeps the network sane. It's also where reality leans on a promise we make to ourselves. Now tie this back to the threads we've been pulling. SN 1987A's neutrinos beat the light not by breaking C, but by leaving first and traveling differently. To compare arrivals, we mapped local clocks into a global time by Einstein's rule. The story holds because supernova physics and good synchronization agree. Pioneer's Doppler residuals were a two-way triumph, translating them into where the probe is right now. Folds in Earth orientation, station locations, media delays, and the same synchronization underneath. Quantum Bell tests sort coincidences by time tags disciplined under that convention and overlay light cones drawn with a C we know from round trips. None of this undermines relativity. It strengthens it by making the contract explicit. The invariant content, the stuff no coordinate choice can touch, is built from local measurements and round trips. The seductive content, now across the galaxy, instant coordination, earlier by hours, rides on how we chose to set distant clocks. That's the glitch worth naming, not a broken wall, a seam. The speed of light is a hard budget for messages you can control. The one-way value that lets you line up distant tapes is a definition that has never betrayed us, and might never, but remains a definition. There's a reason textbooks keep this in the basement. In careful hands, it's unexciting. Change epsilon everywhere and you get the same answers. In clumsy hands, it sounds like license to say anything. We're not throwing a party for ambiguity. We're putting a label on the contract we signed in 1905 so we can recognize it when anomalies press on the edges. Because the next arenas, horizons that look like render boundaries and vacuums that aren't empty, depend on how the budget is enforced, not on breaking it. The wall as a refresh rate, computational universe framing.